So let's take a look at areas between curves. Now, finding areas between multiple curves is going to be one of the first applications of integrals that we're looking at. So let's say we have a top function here, or a top curve, f of x. And I'll just put another color, a bottom curve here, g of x. And then we have our two bounds, so our left bound here is a, and our right bound here is b. And basically we're trying to find the area in between those two curves. Well, in the formula to find the area in between those two curves is going to be the area equals the integral from our left bound or our bottom bound to our top bound, so from a to b, of the top curve minus the bottom curve. So in this case, f of x minus g of x times dx. Now, if I draw another graph, let's say in this case I have a right curve. Let's go ahead and label that f of x. And then I have a curve on the left. Let's go ahead and label that g of x. And I'm trying to find the area in between those two curves. Well, in this case, realize that there's not a top curve and a bottom curve, but there is a right curve and a left curve. So the formula I have to use in this case is going to be the area equals the integral. Now, in this case, because there's a right curve and a left curve, we'll use y bounds, and we'll put everything in terms of y. So let's call this c and d. So the area equals the integral from c to d of, now once again we have to put everything in terms of y. So we take the right curve minus the left curve in this case, so f of y minus the left curve, which is g of x, but we need to put everything in terms of y, so f of y minus g of y times dy, because once again our variable of integration is the y variable. So the main thing to take away here is when you have the top curve and bottom curve, you just take the top curve minus the bottom curve, the integral of that, and our bounds must be x bounds. And if you have a right curve and a left curve, you're trying to find the area in between those two curves, then you take the integral of the right curve minus the left curve, and you use y bounds in that case, and your variable is y. Now f of y and g of y, once again, all we're doing is we're just putting the entire function in terms of y. Now for these next set of problems, let's go ahead and find the area of the region. So for number 1, we have the top curve, which is marked in red, that's going to be y equals 5x minus x squared. And the bottom curve in blue is going to be y equals x. And we're basically trying to find the area of the region in between those two curves. And notice the pointed intersections of both of those curves are 0, 0 at the origin, and then right at 4, 4. So because we have a top curve, y equals 5x minus x squared, and a bottom curve, y equals x, we can go ahead and use the formula where the area equals the integral from the x bounds a to b of f of x, the top curve, minus g of x, the bottom curve, times dx. So in this case, we can rewrite the formula, area equals the integral. Now for our bounds, remember those are going to be x bounds because we have top curve minus bottom curve, and the x bounds range from 0, 0, the origin, to 4, 4. So our x bounds range, if I go ahead, from 0 to 4. So we can say the integral from 0 to 4 of the top curve. Remember, because we have top curve minus bottom curve, we can put everything in terms of x, which it already is put in terms of x, so we can just leave it as it is. Of 5x minus x squared, once again that's the top curve, minus the bottom curve. The bottom curve is y equals x. So just minus x times dx. And then we can just go ahead and evaluate from there. So 5x minus x is 4x, so I can simplify it down into the area equals the integral from 0 to 4 of 4x minus x squared dx. Now we can go ahead and integrate, so the integral of 4x is going to be 4x squared over 2, and then minus the integral of x squared, which is x cubed over 3. Now 4x squared over 2 can be simplified down to 2x squared, so we have 2x squared minus 1/3 x cubed. So now that we have integrated, we can evaluate from our bounds of 0 to 4. So when I plug in 4 first for x, we have 2 times 4 squared, which is 16, minus 1/3 times 4 cubed, which is 64. And then minus, when I plug in 0 for x, we have 2 times 0 squared, which is 0, minus 1/3 times 0 cubed, that's still going to be 0, so that will cancel out. Now 2 times 16 is 32, minus 1/3 times 64, 64 over 3. So then we can simplify this to just make one whole fraction. I can rewrite 32 as 96 over 3. So 96 over 3 minus 64 over 3 is going to give us exactly 32 over 3. And that's the final answer. Now for number 2, notice our two curves here, there is x equals e to the y, and there's x equals y squared minus 2. And our two y bounds here are going to be y equals 1 and y equals negative 1. So in this case, realize that there's not a top curve and a bottom curve, but there is a right curve and a left curve. So we have to use the formula where we put everything in terms of y, and area is going to equal the integral from c to d, once again those are just our y bounds, of the right curve minus the left curve. So f of y, that's the right curve put in terms of y, minus g of y, the left curve put in terms of y, times dy. Now realize that both of our curves are already in terms of y, so we're good to go, and we can just plug everything into the formula. So the area equals the integral. Now our bottom y bound is negative 1, our top y bound is 1, because this is the area we're looking for, the area shaded in yellow. So we're going from the integral from negative 1 to 1 of the right curve put in terms of y, that's going to be e to the y, minus the left curve put in terms of y, so minus y squared minus 2, and then times dy. So now I can go ahead and simplify this integral just a little bit. So from negative 1 to 1 of e to the y minus y squared plus 2 times dy. So when I integrate, the integral of e to the y is just going to be e to the y. The integral of negative y squared is going to be negative y cubed over 3. And then we have plus the integral of 2, and the integral of 2 is just going to be 2 times y. Now we can evaluate from negative 1 to 1. So when I plug in 1 for y, we get e to the first, which is just e, minus 1 cubed over 3, that's my negative 1/3. And then we have plus 2, minus, when I plug in negative 1 for y, we get e to the negative first, minus negative 1 over 3, which is going to be plus 1 over 3. And then we have minus 2. So now simplifying, we have e minus 1/3, and then plus 2. I'm going to distribute over the negative to the right set of parentheses. So negative e to the negative first, minus 1/3, and then plus 2. So then we have e to the first minus e to the negative first, so e minus e to the negative first. We have negative 1/3 minus 1/3 is going to be negative 2/3. And then we have 2 plus 2, which is going to be 4. So then to simplify, I can rewrite 4 as 12 over 3. So then we have e minus e to the negative first. I can also write that as 1 over e. And then we have negative 12 over 3 plus 12 over 3. That's going to be positive 10 over 3. That's the final answer for the area in between the two curves. Now for number 3, we aren't given a graph, but we are given two functions here, y equals x and y equals x squared. So it's a good idea to actually graph these two functions. So if I go ahead and graph this, we have y equals x squared, which might look something like this. And then we have y equals x, which might look something like this. And I apologize for my drawing, but this really is supposed to touch at the origin. And we have another intersection point there. And basically what we're trying to find is the area in between those two curves. Now notice in this case we do have a top curve, y equals x, and a bottom curve, y equals x squared. So we can go ahead and use the formula where we take the integral of the top curve minus the bottom curve. And both have to be in terms of x, because once again we're doing top curve minus bottom curve. So the top curve is y equals x, minus the bottom curve, y equals x squared, times dx. And all we have left to do now is to find our bounds of integration. And because our variable is x, we have to find the x bounds. Now notice the lower x bound is 0, and we need to find what the top x bound is. But the top x bound is where those two curves intersect. So to find that intersection point, we can set those two curves equal to each other. So x is equal to x squared. So now what I can do is go ahead and subtract over the x. So 0 equals x squared minus x. I can then factor out an x, so x, or 0 equals x times x minus 1. And then I can go ahead and set each of those factors equal to 0. So x equals 0, and if x minus 1 equal to 0, then x equals 1. So one of our intersection points, as we've already mentioned before, is at x equals 0. The other intersection point is at the x value of 1. So then I can go ahead and say the area equals the integral from 0 to 1 of x minus x squared dx. Now let's go ahead and integrate. So the integral of x is going to be x squared over 2. And then we have the integral of negative x squared, which is negative x cubed over 3. And then we can go ahead and evaluate from the x bounds of 0 to 1. So when I plug in 1 for x, we get 1 squared over 2, which is just 1/2, minus, we have 1 cubed over 3, that's 1/3, minus, when I plug in 0 for x, we just have 0 squared over 2, which is 0, minus 0 cubed over 3, that's also 0. So that will cancel. So all we're left with is 1/2 minus 1/3. I can go ahead and combine those two fractions. So I can turn 1/2 into 3 over 6, and turn negative 1/3 into negative 2 over 6. So then 3 over 6 minus 2 over 6 gives us the final answer of 1 over 6. Now for number 3, we have y equals 1 over x, y equals 1 over x squared, and x equals 2. So the very first thing, as always, is to go ahead and graph this. So if I go ahead and graph these three curves, we have y equals 1 over x. So 1 over x, I'm just going to mark in blue, is going to look something like this. So let's go ahead and label that 1 over x. And now for y equals 1 over x squared, that might look something like this. So it's very similar to 1 over x, just a little bit steeper at first. So that's going to be y equals 1 over x squared. Once again, I apologize for my drawing, but really what we need to focus on is the first quadrant only. So, and the next curve is x equals 2. So let's just say that's 1, that's 2. So x equals 2 is going to look something like this. So basically the region or the area we're looking for to find is right here, in between those two curves and the x equals 2 curve. So now what I can do with this is actually go ahead and zoom in to the graph. So I'm only going to draw the first quadrant. So y equals 1 over x, let's go ahead and just start with that. It's going to look something like this. So go ahead and label that y equals 1 over x. Then y equals 1 over x squared might look something like this. So I'll label that y equals 1 over x squared. And then finally we have x equals 2, which is going to be somewhere around here. So once again, we're looking for this region here. Notice we do have a top curve and a bottom curve, so we can use the formula where the area equals the integral of the top curve, which is in terms of x. Now y equals 1 over x is the blue curve that's on top. So we have 1 over x minus the bottom curve. The bottom curve is the red one, 1 over x squared, and then times dx. So now all we need to do is find our bounds. So realize that our bottom bound has not been found yet, but our top bound is at x equals 2. So the top bound is 2. Now in order to find the bottom bound, we can already kind of guess that it's 1. But just to double check, we can set those two equations equal to each other. So 1 over x equals 1 over x squared. So if 1 over x equals 1 over x squared, in order to solve this, I'm just going to multiply both sides of the equation by x squared. So if we have x squared times 1 over x, we'll get x on the left side of the equation equals, we have x squared times, or 1 over x squared times x squared, which just cancel and we get 1. So at x equals 1, like we said before, there is another intersection. So our area is the integral from 1 to 2 of 1 over x minus 1 over x squared dx. Now in order to solve this, the integral of 1 over x, remember, is the natural log of the absolute value of x. And then we have minus the integral of 1 over x squared. So I'll rewrite it as the integral of x to the negative second power. Because now we can use the power rule, and then we get x to the negative first over negative 1. That's basically going to be negative 1 over x. So if we have minus negative 1 over x, that's going to be plus 1 over x. And then we can go ahead and evaluate from the x bounds of 1 to 2. So when I plug in 2 for x, we get ln absolute value of 2 plus 1/2. And minus, when I plug in 1, we get ln absolute value of 1, and then plus 1 over 1, which is 1. Now ln of 1 is 0, that will cancel. We have ln absolute value of 2, which is just ln of 2, plus 1/2, and then minus the positive 1, so minus 1. Now 1/2 minus 1 is negative 1/2, so we get the natural log of 2 minus 1/2 as our final answer. Now for number 4, we have x equals 1 minus y squared and x equals y squared minus 1. So we can't necessarily graph this right now because we don't know what those graphs look like, more than likely. So what we have to do first is isolate y and solve for y so that we can actually graph it. So negative y squared, or actually I'm going to add over the y squared and then subtract over the x. So we get positive y squared equals 1 minus x. So then y equals plus or minus the square root of 1 minus x, or negative x plus 1. Now for the second equation here, if I go ahead and isolate y squared is going to equal x plus 1. And then if I isolate y and take the square root, y is going to equal plus or minus the square root of x plus 1. Now if I were to graph both of these functions, let's just start with the right one here. Y equals plus or minus the square root of x plus 1. And let's just focus on the positive version, so cancel out the negative version. Now if we were to graph y equals just the square root of x plus 1, that's just y equals the square root of x, but shifted to the left 1. So it might look something like this. Now the negative version, y equals a negative square root of x plus 1, is just going to be a reflection across the x-axis. So this is going to be the graph of y equals plus or minus the square root of x plus 1, or x equals the y squared minus 1. I'll write that down. Now for the second equation, we have y equals plus or minus the square root of 1 minus x. Same thing, I'm just going to focus on the positive version first. So y equals the square root of 1 minus x. And really what that is basically a backwards square root of x function, just shifted to the right one. So it might look something like this. And then the negative version, once again, is just a reflection across the x-axis. So it might look something like this. And so that is going to be y equals plus or minus the square root of 1 minus x, or x equals 1 minus y squared. So the area we're trying to find in between those two is right about here. Because there is a right curve and there is a left curve, we have to use the formula where the area equals the integral of the right curve minus left curve. So area equals integral of the right curve. Now the right curve is in blue, and because we're doing right curve minus left curve, we have to put it in terms of y, which it already is. So we put 1 minus y squared minus the left curve's in red, that's y squared minus 1. And then multiply by dy. Now in order to find our bounds of integration, once again these are y bounds because we're integrating with respect to y. So our y bounds here. Now in order to find those y bounds, all we have to do is set the two functions equal to each other. So if 1 minus y squared is equal to y squared minus 1, I can go ahead and add over the y squared. So we get 2y squared equals, I'll add over the 1. 1 plus 1 is 2. Divide over the 2's, they will cancel. So y squared equals 1, and then y equals plus or minus the square root of 1, which is plus or minus 1. So our two intersection points, y equals negative 1 and y equals 1. So our area is equal to the integral from negative 1 to 1 of 1 minus y squared minus 1 dy. Now if I go ahead and simplify the integral before evaluating, integral from negative 1 to 1 of, we have 1 minus y squared minus y squared, I'll distribute the negative, plus 1. So then we have the integral from negative 1 to 1 of 1 plus 1, which is 2, and then we have minus 2y squared times dy. So now evaluating the integral of 2 with respect to y is going to be 2y, and then we have the integral of negative 2y squared with respect to y, which is negative 2y cubed over 3. And then we can go ahead and evaluate from the y bounds this time of negative 1 to 1. Now when I go ahead and plug in the top bound 1 for y, we'll get 2 minus 2 times 1 cubed over 3, which is minus 2/3, minus, when I plug in negative 1 for y, we get negative 2 minus negative 1 cubed is negative 1, negative 1 times 2 is negative 2. So we have minus a negative 2/3, which is going to be plus 2/3. So now we have 2 minus 2/3. I'll distribute the negative, so plus 2 and then minus 2/3. Then 2 plus 2 is 4. We have negative 2/3 minus 2/3 is negative 4/3. In order to simplify, I'll combine those two terms to create one whole fraction. So 4 can be written as 12 over 3. So we have 12 over 3 minus 4 over 3, which gives us the final answer of 8 over 3. That's going to be the area in between those two curves.